All right, today we are diving deep into the architecture that powers pretty much everything cool these days, from gaming to artificial intelligence. Of course, I'm talking about the Graphics Processing Unit, the GPU. We're going to build a kind of blueprint, showing you exactly how the CUDA software model tells a programmer's instructions what to do and turns them into the massively parallel workhorse that is the modern GPU.
So let's start with the big question, right? Here's the fundamental problem. If you need to do just a few really complex things, one after another, your standard processor is fantastic. But what happens when you need to do thousands or even millions of pretty simple things all at the exact same time? Well, that is the question that GPUs were born to answer.
And the answer? It lies in a completely different design philosophy. Think of a CPU as a specialist, right? We call it the host processor. It's got a handful of very powerful, really smart cores that are perfect for handling complex, sequential tasks. A GPU, on the other hand, we call that the device. And it's not a specialist, it's an army. It has thousands of simpler cores, and every single one is designed to do just one small part of a massive, parallel job.
So here's our game plan. We'll kick things off with that core problem of parallelism. Then we'll see how programmers use a software hierarchy to get a handle on it all. From there, we'll actually map that software onto the physical hardware, navigate the tricky memory maze, uncover some of the biggest performance pitfalls you have to avoid, and finally, we'll take a little peek into the future of how these two processors are going to work together. You see, it all boils down to this relationship. The CPU, our host, is running the main program. But when it hits a task that's just computationally massive, like processing every single pixel in a high-resolution image, it packages that job up into something we call a kernel and just hands it off to the GPU to be executed in parallel by its giant army of cores.
So how on earth does a programmer organize millions of parallel tasks without going completely insane? Well, the answer is the CUDA programming model. It gives you this logical blueprint, this really beautiful hierarchy that makes all of this complexity totally manageable. So let's start peeling back the layers.
At the very, very top of the hierarchy, you have the grid. When you launch a kernel, you create one grid. Think of it as the entire construction project. Every single task that needs to get done is contained right inside this one grid. It's the whole shebang.
Okay, now we zoom into that grid, and we find it's made up of things called thread blocks. A thread block, you can think of it like a single construction crew. These are groups of threads that are guaranteed to run on the same piece of hardware, which is awesome, because it lets them cooperate and share data really, really fast. Now here's the crucial part. Each block has to be completely independent of all the other blocks. And this is just genius, because it means the exact same code can scale up to run on a tiny GPU with just a few processors, or a monster one with hundreds of them. And finally, inside each block, we have the individual thread. This is your single worker on the crew. Each thread gets its own unique ID, which basically tells it exactly which piece of data it's responsible for. It's like saying, hey, you, thread number 57, you're in charge of pixel number 57. Simple as that.
Okay, so we've got our blueprint, a grid of blocks, and those blocks are filled with threads. Now let's see how this logical plan actually gets built, how it comes to life on the physical hardware. How does the blueprint become reality?
Well, the key piece of hardware here is the streaming multiprocessor, or just SM for short. And SM is the GPU's powerhouse, and each thread block, our construction crew, gets assigned to exactly one SM. So you can think of the SM as the foreman, and it's managing that entire crew until its job is completely done. A modern GPU is just packed with these SM.
But here's where things get really, really efficient. The SM, our foreman, it doesn't manage each individual worker one by one. I mean, that would be way too slow. Instead, the hardware bundles them up into little squads of 32, and these are called warps.
32. You got to remember this number. It is the magic number in the GPU world. A warp is always 33 threads. This is the fundamental unit of scheduling. All 32 threads in a single warp execute the exact same instruction at the exact same time, but they do it on their own little piece of data. This is the heart of what's called the single instruction, multiple threads, or SIMT execution model.
But listen, raw processing power is only half the story. To get that mind-blowing performance, all those thousands of threads need lightning-fast access to data. And that means we have to learn how to navigate the GPU's complex memory hierarchy, which is, honestly, a bit of a memory maze.
This whole system is all about trade-offs. At the very top, you've got registers. They're like a worker's personal tool belt. They're super fast, but they're totally private to just a single thread. Next up is shared memory. This is like the Cruise shared toolbox. It's on chip, so it's very fast, and it lets all the threads in a block cooperate. And finally, you've got global memory. This is the main supply depot. It is huge and it's accessible to absolutely everyone, but it's off chip and it's much slower to get to. The real key to performance is keeping your work in that tool belt and that toolbox as much as you possibly can.
And just look at how important that shared toolbox has become. Over the last decade, the amount of super fast shared memory available on each SM has absolutely exploded. I mean, from 48 kilobytes on the Kepler architecture all the way up to 228 on Hopper. This is no accident, folks. It's a direct reflection of just how critical that fast, on-chip cooperative memory is for feeding this hungry beast of a process.
So, with this whole architecture of execution and memory, certain rules start to emerge. And if you follow them, you get incredible speed. But if you break them, well, you're going to hit some serious performance pitfalls. Let's look at two of the absolute biggest ones.
The first big one is something called warp divergence. Remember how we said all 32 threads in a warp execute in lockstep? Well, what happens if your code has an if-else statement? The warp literally splits in two. First, all the threads that met the if condition execute their path, while the else threads just sit there and wait. Then they switch. The else threads execute their path while the if threads wait. You are effectively running at half speed, idling half of your expensive hardware. This serialization is a massive performance killer.
Now, for the good news. The best-case scenario for memory access is called memory coalescing. This is what happens when all 32 threads in a warp need to access 32 times adjacent locations in that big global memory. The hardware is smart enough to see this pattern, and it can just grab all of that data in one single wide, super efficient transaction. It's beautiful. It's perfect teamwork.
And then there's the opposite, uncoalesced access. This is chaos. This is when threads in a warp need data from all over memory, just scattered, random locations. Now the hardware has to make a whole bunch of separate, tiny, inefficient trips to memory to try and satisfy all those requests. It's a mess. It wastes a massive amount of memory bandwidth, and it can absolutely destroy your performance.
And you know, this entire model, it's not standing still. It's constantly evolving. The latest architectures like NVIDIA's Hopper and Blackwell, they're introducing brand new features that push the boundaries of cooperation even further. One of the biggest new ideas is the thread block cluster. This actually adds a whole new layer to our hierarchy. What it does is it allows groups of thread blocks to be scheduled together and, more importantly, to communicate directly with each other using a new type of super fast memory called distributed shared memory. It's kind of like allowing different construction crews to share their specialized tools directly without ever having to go back through that slow main supply depot. It's a game changer.
So let's pull this all together. Why does any of this matter? Well, the CUDA hierarchy is what makes programming thousands of cores manageable in the first place. Understanding how that software blueprint maps to the hardware, to the SMs and the warps, that's what lets developers write truly fast code. And most of the time, the biggest performance wins come from mastering that memory maze and avoiding those critical pitfalls, like warp divergence and uncoalesced memory access. What we're looking at is an incredibly powerful and intricate system. It's one where the software design and the hardware reality are just deeply connected. Which really just leaves us with one final huge question. As this relationship becomes even more tightly woven, what truly massive computational problems in science, in AI, in medicine, problems that we once thought were flat out impossible, might we finally have the blueprint to solve?